In this quick video, we're going to do a basic refresh on factoring. Now, there's technically lots of different factoring we could do. I'm just going to go through a couple right now, but know that we will discuss factoring more in depth as the year proceeds, and there are more ways to factor than just what I'm doing right here. Okay, so the first thing we always want to check when we factor is if we have what's called a GCF, or a greatest common factor. So on number 12 that I have here, I'm going to look for that greatest common factor. Do these three terms, the 21, the 42v squared, and the 7v to the third, do they have anything in common? Now, what they have in common, it could be a number, it could be a variable, or it could be both. So if I look at the numbers, it seems to be that all of them have a factor of 7. So I can include 7 as my GCF. So I'm going to write that 7 down. Now, if I think in terms of variables, there is not a variable that all three terms have. 2 of them have v's, but the first term does not have a v. So this particular polynomial does not have a variable GCF. It's only a number. Now, once I have determined what my GCF is, I need to what we call factor it out of the expression. When I say factor it out, technically what I'm doing is I'm dividing it out of each term. So what I'm actually doing is taking this GCF and I'm dividing it out of all three terms. When I do that, 21 divided by 7 gives me 3. Negative 42v squared divided by 7 gives me negative 6v squared. And 7v to the third divided by 7 just gives me 1v to the third, or just v to the third. Now, GCF factoring is set up in such a way, if you wanted to check your work, you could just distribute that 7 back out, and you should end up with what we started with. Okay? Now, if I move on to the bottom. Again, we forever and always check a GCF. So if I look at number 13, do those two terms have anything in common? The reality is that they do not. So once I've moved past GCF factoring, I'm looking at other strategies. Because those are two terms, the only other way you know of right now to factor two terms is what we call a difference of squares. So let's kind of walk through that criteria and see if this fits into that criteria. To be a difference of squares, you have to have subtraction, which we do. You have to have two terms, which we do. And both terms have to be perfect squares. 25n squared is a perfect square, and so is 16. So this works. Once I've figured out that we meet the criteria for difference of squares, then it becomes making sure I know the pattern as to how that actually factors. A difference of squares factors into two binomials, so that would be two sets of parentheses. In the beginning of each set of parentheses, I take the square root of the first term. So the square root of 25n squared is 5n. So that goes in the front of each set of parentheses. In the back of each set of parentheses is the square root of the second term. The square root of 16 is 4. That goes in the back of each set. And then in the middle, one's a plus, one's a minus. The order doesn't really matter. So I just have to make one of these sets of parentheses a plus and one a minus. It doesn't matter which is which. I could have put the subtraction first and then the addition. Doesn't matter. Now again, if I multiply these out, if I FOILed these out, I would end up with what I said. Okay, moving on to the last two are probably the most difficult to maybe remember. As always, I'm checking a GCF. So I'm looking at number 14 at those three terms. Do they have anything in common? And unfortunately, number and variable-wise, they do not. So at this point, because this is different than number 13, this has three terms. That's what we call a trinomial. Trinomial factoring is a little bit different. It's kind of like a puzzle. I'm looking to figure out a pair of numbers that multiplies to one thing and adds to something else. So the question becomes, what am I trying to multiply and what are we trying to add to? Well, in order to figure that out, I'm always going to take, if I look at the first coefficient times the last. So in front of a squared, there's no number, so there's the 1 there. And the last number I see is 18. So I'm talking about those two numbers. I need to multiply them together. 1 times 18 gives me 18. So my goal number for multiplication is 18. My goal number that I'm trying to add to is whatever in the middle, which in this case is 11. So I am looking for a pair of numbers that multiplies to 18 and adds to 11. So at this point, I really need to know factors of 18. It just so happens that the two numbers that multiply to 18 and add to 11 are positive 9 and positive 2. The order that you write those does not matter. Now, once I've figured out those numbers, those are the keys to factoring this trinomial, meaning this is going to factor into two binomials similar to the last one. If my numbers were positive 9 and positive 2, then my factors become a plus 9 and a plus 2. Again, the order doesn't matter. I could have put the a plus 2 first and then the a plus 9. Either way, if I multiplied these binomials, I would end up with the original trinomial that I started with. Okay, if I look down to number 15, 15 is a little bit trickier just because there's a lead coefficient that isn't 1, meaning if I look at how this starts, it starts with a 2. But forever and always, I check a GCF first. Do those three terms have anything in common? Again, they do not, so I have to move on to a different strategy. Now, I'm going to start out like I did before. Once I recognize that this is a trinomial, I'm going to try to unlock this puzzle of figuring out what do I need to multiply to, what do I need to add to, and what are my numbers. So once again, take the first coefficient times the last. 2 times negative 28 is negative 56. So I'm trying to multiply to negative 56. I'm always trying to add to that middle term. Nothing in front of k, so that's positive 1. So then I am looking for my numbers. So I'm looking for two numbers that multiply to negative 56 and add to 1. So the pair of numbers that I end up needing are going to be positive 8 and negative 7. So this is going to start very similar to my last one. What I mean by that is my numbers are positive 8 and 7. Sorry, my screen stuck a little bit. There we go. I'm going to use that, but I'm going to use it in a slightly different way. Because of that lead coefficient, what I have to do is I kind of have to trick this problem into working for me. So the first thing I'm going to do is I'm going to take that middle term and I'm going to kind of rewrite it. Instead of a positive 8k, I'm going to make it a positive 8k minus 7k. Now, I want you to understand that those two things mean the same. Plus k is the same thing as 8k minus 7k. Then what I'm going to do is I'm going to bring those other two terms right down. I'm going to bring that 2k squared down on the front. And I'm going to bring that minus 28 on the back. So understand all I did was take my two numbers. I replaced the original middle term with something that was equivalent. So then you're thinking, well, why did you do that? Because that's not what I did last time. The reason I didn't do that last time is because I didn't have a lead coefficient. Because I did here, I need a slightly different process. So now what I'm going to do is I'm actually going to group these four terms together. I'm going to group the first two together, and I'm going to group the second two together. And what I am looking for is a GCF out of each group. They will be different GCFs. So my first group, the 2k squared and the 8k, they have a GCF. Their GCF is 2k. Now, if I divide that GCF out of each term, 2k squared divided by 2k is 1k of this k. And 8k divided by 2k is 4. Now, if I look at the second group, it will be a different GCF. If I look at negative 7k and negative 28, it has a GCF. Its GCF is 7. Now, one thing to be aware of here, if that second group leads with a negative number, then its GCF should also take the negative form. So because this second group is leading with a negative 7k, I want to make my GCF negative 7. Now again, I'm going to take that GCF and divide it out of each thing. When I do that, I get a positive 1k, which is positive k, and a positive 4. Now, you will notice that those two sets of parentheses here are the same. That's good. That helps tell me that I'm on the right track. Because ultimately, I want my final answer to look like it did in the previous problem. I wanted to have two sets of binomials. So I am almost there. Now, I'm going to do one more GCF factoring. I know this looks funny, but technically, this is only two terms. This is a term, and this is a term. So if I look at each of these terms and ask myself, do they have a GCF? do they have anything in common? The answer is yes. They both have a k plus 4. So I'm going to factor out that k plus 4. And then if I think about what's left over, if I divide k plus 4 out of the first term, I am just left with 2k. If I divide k plus 4 out of the second term, I am just left with minus k. Or I'm sorry, minus 7. Okay, and here again, if I FOIL this out, I should end up with what I started with. Now, that process is a little more lengthy when you have a Lie coefficient that's not 1, and quite honestly, there are other ways to do this. So if you are more comfortable with another way, I'm good with that. Just a refresh.